Swayam Prabha. Digital India. Educated India.
We have just discovered the two laws are simply two statements. U, S are functions of state. With that you have all the classical derivations in essentially all of mechanical engineering, all of heat work conversion devices. All the results can be derived by just making this statement. The natural corollary is, and if you are an inquisitive student, is there a third law? Is there another property that is a function of state? So far nobody has found out anything except by adding, subtracting. Now you can do U minus Ts, you can do U plus PV minus Ts, you can play games. You already know some functions of state, that is these are known to be functions of state. Composition are functions of state. This is mole fraction, I will say the set of compositions are functions of state. This is known by observation, okay, by observation. These are known to be functions of state. By observation you know that Q and W are not functions of state. Essentially the two laws said these are the only observable properties, and it said while Q and W are not functions of state, I can find two functions of state that are related to Q and W. One was simply delta Q minus delta W, which is du, or U equal to Q minus W for a closed system, and the other, which is much more subtle, was this entropy. The second law is probably the greatest discovery of the 19th century. So basically the concept here as far as entropy is concerned, entropy is a very profound concept, and what you have is, apart from these functions of state, you have other functions of state that keep occurring again and again. As far as chemical engineering is concerned, or chemical engineering and chemistry if you like, we have another additional functions. The other functions of state that they have found are only combinations. You have U minus Ts, which is called A, you have U plus PV, which is called enthalpy, and then H minus Ts, which is called the Gibbs free energy. You can generate any number of them, you know, if you are perverse you can put T power half here, that is also a function of state. Any function of a function of state is a function of state. So you can combine any number of these and produce these, and only you will be interested in them. I mean, if sufficient number of people get interested, gets a name. So this is Helmholtz free energy. Turns out this is very important. I will show you that very quickly, why this is of great importance. Similarly enthalpy is very important in some cases. The free energy, Gibbs free energy, very important in some cases. Specifically I will tell you what results we are going to show. When you are looking at equilibrium, I am going to show, depending on the variables that I have held constant, if you are looking at systems with constant T and V, constant temperature, constant volume, I will show that equilibrium is attained when A is a minimum. Therefore A is important, keeps coming again and again. I am going to derive this result. I am going to show you that whenever T and P are held constant, pressure and temperature, which is what happens in flow processes in the chemical industry, equilibrium is attained when G is a minimum. Therefore A and G are very important. Actually you could use U and H. You can show that U is a minimum when V and entropy are held constant, but you do not have an entropy meter, so there is no way you can stick a meter and say this process has entropy constant. You can talk about adiabatic processes, but it is not the same thing as an isentropic process. Similarly you can use enthalpy if it is S and P that are held constant. So we will show these results, but the useful results are those in which the constraints are meaningful. T and V being constant, very meaningful for closed systems. T and P being constant are very meaningful for open systems. The other result that you will get is that in an isothermal system the maximum work you can get out of a closed system is the change in the Helmholtz free energy. That is of great interest. What is the maximum work you can get out of a system, or what is the minimum work you can get away with? It is not a student phenomena alone, even the most profound scientists are looking for what is the minimum work they can get away with, but they are asking much more deeper question than just questions of laziness. But actually it is not a bad idea to do the minimum work and get maximum results, but you have to do it, you have to integrate it over a 50-year period. Now if you are looking at very short term gains, then you play the penalty later, that is all. Delta G again is the maximum work you can get out of a system, actually minus delta G, there will be sign changes, but the change in the Gibbs free energy is the maximum work you can get out of an isothermal flow system. So these are the only important results in thermodynamics, almost all results are derived out of this, but you are dealing with multi component systems and composition dependence is where there is ambiguity in thermodynamics. So we will get started and discuss U and S as functions of state and discuss the differential relations, and you can do calculus only with functions of state. You can't write equations of calculus with Q and W because they are not functions of state. So the first point is U is a function of S and V. These are natural variables, or let me start off first. The first law tells you du is equal to delta Q minus delta W. I am going to deal with closed systems. And then depending on the system that you are dealing with, which is PVT, so called PVT systems, which is what you deal with very often, delta W is equal to minus PdV. No, delta W is equal to PdV, sorry, I will leave it as, I will come back to the sign convention. PdV is the work done by the system, delta W is PdV, so this becomes, and delta Q is equal to TdS for a reversible system. I will come back to this. Because delta Q by T was defined as ds. So you get this result, du is equal to TdS minus PdV. This is actually the combined form of the two laws. The second law itself, the laws can be stated very simply. While I said U and S are functions of state, the laws are simply stated like this. You say U is a function of state, that is all, and then you say S is equal to maximum. Now I should rewrite U S, sorry, I should say U of an isolated system is equal to constant, and S for an isolated system always increases. These are actually the statement of the two laws as far as we are concerned. I am going a bit back and forth, but partly because you know some of these results. This is one way of stating it. As far as calculus is concerned, as far as equilibrium systems are concerned, all you need to know is that U and S are functions of state. To derive maxima minima, you have to make the statements in terms of the laws itself, and once you have said this, let me rewrite this in a slightly different fashion. This is all right, I will have to rewrite this. Suppose I have a system and then I have surroundings. And I have an exchange of heat between the system and the surroundings. Now if the heat is coming into the system, the surrounding temperature has to be higher than the system temperature. So let me say T surroundings greater than T system, then delta Q is greater than 0. everything, all the signs refer to the system of interest, not to the surroundings. So when I say delta Q greater than 0, that means the system absorbs heat. The convention I use is that if heat is absorbed, it is positive. If work is done by the system, it is positive. The new books have an opposite convention. Work done on the system is taken as positive, but in terms of these variables, so mine would be delta W is equal to PdV according to the new IUPAC convention. It is not really new, it is more than 20 years old, but lots of books use either convention. The convention is that anything that increases the energy of a system is positive. So if work is done by the system, it loses energy, so work done on the system is considered positive, so you will find a minus sign here, but those that have a minus sign here will have a plus sign here. So in terms of measurable variables, the equations will be the same. You just use any convention you want, but be consistent, and I am not going to trick you by asking you is it by or on, and you can figure that out by common sense. So if this is true, if delta Q is the delta Q by T, T system will be just defined as T. Delta Q by T is the energy absorbed by the system, and if I take the surroundings, delta Q surroundings by T surroundings is greater than or equal to 0, because the surrounding plus system constitute an isolated system. The law is valid only for an isolated system. This delta Q surroundings is equal to minus delta Q, because as far as surroundings is concerned, the heat that it receives is the heat lost by the system. So and dq by T, delta Q by T is defined as ds, talking about differential change in differential quantity of heat being transferred. Therefore I do not have to worry about whether the actual process is reversible or irreversible. So I have ds minus delta Q by T surroundings is greater than or equal to 0, or you get T surroundings times ds is greater than or equal to 0. You have to find the smallest value of T surroundings for which it is valid for you to generalize the result. The smallest value of T surroundings for heat absorbed by a system would be equal to T itself, right. This the most general case is T ds is greater than or equal to 0. If T ds is greater than or equal to 0, then T surroundings ds is automatically greater than or equal to 0. I am sorry, T d is greater than delta Q, not 0. Keep. So the real law for closed systems for all kinds of processes, this is equal to, this is less than or equal to T ds minus delta W. This is the combined form of the two laws. And since your first quantity of interest is work, you rewrite this and ask what is delta W, it is less than or equal to T ds minus du. So delta W itself at constant s, suppose I held s constant in a process, delta W has to be less than or equal to du minus du. So the maximum value of delta W can only be equal to minus du. So absolutely trivial result. but if I know a system goes from state 1 to state 2 and I know the difference in the internal energy, minus of that is the maximum work I can get out of the system at constant entropy. But this is not the most useful way of writing it. You rewrite this as, you write T ds minus d of u minus Ts, sorry, not T ds, minus STT. Sorry, I will rewrite this way. This gives you du minus TdS, I will put a minus sign here, this gives you minus du plus TdS, and then I have plus SDT, so I will subtract minus SDT. And because this animal u minus Ts is going to appear again and again, I will write this as minus dA minus SDT. So I have this profound conclusion, delta W at constant temperature maximum value is minus dA, and since most processes occur under isothermal conditions, in the sense that you may have a closed system, you start at room temperature, you may heat, cool, do whatever, finally you come back to room temperature. So if I take the whole process, the change maximum work I can get out of the system is minus the change in Helmholtz free energy. Therefore, it is of great interest to know how the Helmholtz free energy varies with the state of the system. In the case of open systems, the derivation is not as simple, but let me state it in any case. There are two more results that you can easily see. I can write d of u plus PV minus d of PV. So instead of this, I can rewrite this equation. I can rewrite this equation in terms of H, enthalpy. I can also rewrite it in terms of Gibbs free energy, which is H minus Ts, but it is not useful in closed systems. In closed systems, these are the two useful results. I am now going to look at open systems. In an open system, I have something coming in and something going out. Again, thermodynamics only, however complex this may be, all I need is one box and one line in, one line out. So if I have a system that exchanges heat again and also exchanges work with the surroundings, you don't quite realize how liberated you are. You do not have to draw one more arrow, because all exchanges with the surroundings can only be in terms of heat or work. That is where Joule liberated you. You did not have to look for one more way of exchanging energy. We have mass coming in and mass going out. What I do in this case, very simple. I think I will draw a more complicated picture, means two lines. What I have marked here is the amount of mass. Suppose I am considering a system between T and T plus delta T, this is time. I am going to consider an open system between T and T plus delta T. The open system actually consists of the following. My open system is simply contents of box. The box could be a whole factory, could be anything. This is my system. I have a system into which mass comes in, mass goes out. Now I consider this open system between time t and t plus delta t. I will write time here. This is du. What I want to do is to calculate, I want to calculate du. I know du closed system is equal to delta q minus delta w. When I write C here, it is closed system, this I already know. I want to relate this closed system du to the open system. It is very easy. For a closed system, I just have to concentrate on the same mass elements. So at time t, I take everything that is in the box plus the mass that would have come in, and then at time t plus delta t this has already come in but some mass has gone out. So I take the contents of the box plus the mass that went out. So my closed system is the following, which is why in Den B for instance he does not bother to deal with open systems in great detail, because you can always derive results for open systems in terms of closed systems. So I am going to define a closed system. A closed system does not exchange mass with the surroundings. I need a closed system only between t and t plus delta t, some small interval of time. This is equal to mass in box plus mass that would have entered between t and t plus delta t. Mass in box at t. This is also equal to mass in box at t plus delta t plus mass that left between t and t plus delta t. So what is du closed system is equal to u closed system at t plus delta t minus u closed system at t. This delta t we will treat as, eventually I am going to take a differential change in time, dt if you like. What is this equal to? U closed system at t plus delta t is u of the open system at t plus delta t. For open system is my system of interest, so I do not put any subscript on it, plus mass that left. What is the mass that left? It is the rate at which mass is leaving into delta t or dt into u. This is small u is the specific internal energy of the mass that is leaving, which means it is the internal energy per unit mass. M dot is the rate times dt is the total mass that left, that multiplied by internal energy per unit mass, minus, this is the first part. What is u closed system at time t? It is this, which is u for the open system at time t, that is the internal energy, total internal energy of the contents of the box at time t, plus this may be different, m dot in may be different from m dot out. It is not necessarily a steady system that I am talking about right now. You have the same interval of time dt times u in. So this u t plus delta t minus u of t is du, plus you have this is equal to delta q minus delta w. Now I also have the second law, which tells me that T ds for a closed system is greater than or equal to delta Q. You must realize that the second law really tells you that T reservoir, right, or surroundings times ds for a closed system. We replace T reservoir by T when we wrote the law as a limiting case. If I have an open system, I must allow for the fact that the temperature here can be different from the temperature here. I may be talking of a heat exchanger where typically the fluid comes in at one temperature, goes out at another temperature. So every time I have to take the reservoir temperature as the temperature relating to the stream, the point at which I am doing this calculation in an open system. So if I rewrite this, for example, ds for the closed system would be exactly like before, ds for the open system plus m dot out s out minus m dot in Sn times dt. If I am writing the second law, I have to multiply this by T reservoir. So I get T reservoir times ds plus m dot out S out minus m dot in actually this is sort of I have written it in a, I suppose I have basically written it wrongly because I mean I have not written it wrong, but T reservoir can be different for each of the streams. T reservoir does not mean one temperature. For example, if I had a heat exchanger, the surroundings would be, if I had a shell normal 2 tube heat exchanger, I have one tube inside, one tube outside. If it is counter current, the temperature exchange would happen from two streams at different temperatures. So T reservoir for the system could be the temperature of the system, but this could be T out, this could be Tn, that is this could be the temperature at the outlet, this could be the temperature at the inlet. So I should actually write Tr for every term here. So in the limiting case, which is what you are looking at, you will get T ds plus T out m dot out S out minus T in for an open system. So the combined form of the law for would be du plus, I will write m dot into dt will be dm. So I will write it simply as dm out S out u out minus dm in Sn. This whole thing is du for the closed system is less than or equal to Tds, which is this one here, Tds plus dm out into T out S out minus dm in into T in Sn. This whole thing is Tds for a closed system minus delta W. I have one last step to do. If you have an open system, there has to be work done on the system by something in the surroundings that pushes the fluid in, that is compulsory. Similarly, there is work done by the system in pushing the fluid out. So that is called flow work, and flow work is a compulsory part, it is not useful work that you get out of the system. So it is convenient to redefine delta W in terms of net work plus flow work. So for example, we define this as delta W is equal to delta Ws. S is usually used for shaft work in mechanical engineering. It could be a turbine with a fluid flowing in, fluid flowing out, and the turbine blades rotating. Sometimes written as U, useful work, all these are same. Delta Ws plus flow work, and flow work is easily calculated. Flow work is simply the work done by the system would be pressure at the outlet, V at the outlet, this is specific volume, times dm out. Dm out times V out is the total volume of the fluid that is pushed out, it is pushed out at a pressure P out, so the work done is P into dV, minus of course work done on the system, P in, V in, dm in. This is the definition, okay. So it is not, delta Ws is not a conceptually new quantity, it is simply a useful quantity that is defined by subtracting from the total work done by the system the work done due to flow, net work done due to flow. Very often these two are equal, so in most chemical engineering systems it does not make a difference, shaft work and total work will be the same, but sometimes occasionally those two terms can be very important. So what we do is, instead of this delta W, I write that delta Ws plus P out, V out, dm out minus P in so this is your law for open systems. It can be written a little more elegantly, we will do that in a minute. Actually I think I will stop here and let you ask questions, and then we will I will start from this and show you that at steady state, basically in any process in chemical industry you are only interested in what happens at steady state, because if you are, even if you are working a mechanical turbine, you are not going to operate it for half a second, 2 seconds, so on, you are going to work it at steady state and ask what happens, how much work you can extract from it. At steady state the mass going in will be equal to the mass going out, dm out and dm in will both be equal, and nothing will change in the box. You can have a turbine into which fluid is coming in with a certain kinetic energy, leaving with another kinetic energy, but it will always, the change u will always be the same. So du will be 0, ds will be 0, and you will ask questions about, you can ask questions about delta Ws. You will say how much shaft work can I get out of the system under steady state conditions per unit mass flowing through the system. So we will answer that question. The only concepts so far are simply the introduction of U and S and two laws, those are asserted, I mean they are only uncontradicted human experience so far. Open systems, we wrote the laws down, we said du I just want to complete one small statement. At steady state, du is equal to 0, ds is equal to 0. So you can rewrite this as delta Ws is less than or equal to, say at constant t, delta Ws is less than or equal to constant t, this t reservoir becomes Tn equals to t. So u plus Pv minus Ts is g. So you will get minus of delta g, and this becomes dm. Just call it dm, or we write this as Ws dot by m dot. So the maximum work that you can get per unit flow of mass through the system is equal to the change in the Gibbs free energy with a minus sign. This is also the minimum work you have to put in. So if I had, the nice thing about thermodynamics is it's very nice for the student, but it's absolutely irritating for the industrialist, because here is a guy who has a huge plant that separates air into nitrogen, oxygen and all that, and you go and tell him, oh this is your process, air, nitrogen, oxygen, and you say the work done in the whole process is actually a factory. He's got all kinds of things coming in, going out. This comes in at 25 degrees 1 atmosphere, this each of these is at 25 degrees 1 atmosphere, and you say Ws max that you have to put in is minus delta G. It means G x1 times the G1 for nitrogen plus x2 G2 for oxygen minus that for air. So if you know G for air as a function of composition, you are through with the calculation, and you can get a model, you can write down models, you can write the answer in 2 minutes. You can ignore the fact that he has high temperatures, low temperatures inside. If you are doing air liquefaction, for example, you will go down to liquid nitrogen in lower temperatures, and all that is ignored because this is T, this is room temperature, this is room temperature, that is all that counts. As far as thermodynamics is concerned, you get completely contemptuous of what he is doing inside. You say that is detail, I will not come into your factory, here is an envelope, where does the air come in and where does this come in, that is all you have to ask. So the whole thing is trivial. Now what I want to do now is, I just want to point out here, you can tersely argue that even in non-isothermal systems it is delta G, in isothermal systems reversible processes it will come out to delta H, but delta H can be derived, that Ws dot by m dot maximum in an adiabatic system is delta H can be derived without any concept of reversibility or reverse. We will go ahead with calculations for various systems. The purpose of the entire course will be to calculate thermodynamic properties, the rest of it is practically downstream. So the purpose of the course is simply to calculate changes in internal energy, in Helmholtz free energy, in enthalpy and G. This is work calculations, maxima and minima in work. You have to calculate changes in UA because a closed system under isentropic conditions, under adiabatic conditions, the maximum work you can get is delta U. The maximum isothermal work you can get out of a system is minus delta A, actually the minus sign, minus delta U minus delta A. In a flow system, the maximum work you can get in an adiabatic system, actually the work you can get in an adiabatic system is delta H, minus delta H, and minus delta G for an isothermal flow system. So if I can calculate changes in U, A, H and G, there is no difficulty at all. For pure systems it is trivial, what is difficult is for mixtures. So we will set aside pure substances or systems with constant composition, discuss two cases. And then mixtures. In all these cases we list what are called measurable quantities. Measurable quantities as far as we are concerned would be PV, temperature, you can put in brackets absolute temperature, and then what is measurable, these are not properties, measurable quantities I have written, these are properties. I can also measure Q, the heat, but that leads to a measurement of enthalpy. For example, if I have du for a closed system is delta Q minus delta W, and if delta W is of the in PVT systems you have delta Q minus P dV. So dH is delta Q minus V dP plus V dP. dH is simply du plus d of PV. So I add P dV and V dP, I will get this. So if I make measurements at constant pressure, I can measure changes in H by measuring Q. Therefore H becomes measurable. This is in constant pressure systems. H are changes in H, I will write it as delta H. Really interested in changes in enthalpy. And along with that, it becomes independent of the path under certain conditions. When pressure is constant, it becomes a functional state. You can differentiate it with respect to T and get derivative properties, which we call the specific heats. Cp is an example, Cv is another measurable quantity, C sigma, which is along a saturation line, that is measurable. So all these are measurable quantities, and the rule in thermodynamics is when you derive any expression, if I want you to get du or dA or dH, or incidentally S is not of direct interest here, but you find u and S, then you can calculate these directly. The thumb rule is that on the right hand side, if you get measurable quantities, stop, otherwise you can keep going around in circles and come back to the first part of the derivative. So our purpose will be to calculate changes in terms of measurable properties. And measurable quantities are these, and all their derivatives are considered measurable. So the change in volume with respect to temperature at constant pressure is a measurable quantity. The expansion, volume expansion coefficient is a measurable quantity. Similarly, the change in volume with pressure is a measurable quantity, and so on. All derivatives are considered measurable, although if you ask a PVT guy who is actually making these measurements, it is pure hell. Making accurate measurements at low pressures, for example, is pure hell, because the volume change is negligible and to measure it accurately becomes very, very difficult. What we will do is we will look at only these changes, we will look at when you can express it in terms of PVT. So the basic equation we will deal with closed systems here. If you are looking at systems of constant composition, you need to look at only closed systems. So I will start with du is equal to Tds minus Pdv for PVT systems. We will be looking primarily at PVT systems. Strictly speaking, in thermodynamics you should write dE, which is the total energy, but in thermodynamics you do not worry about changes in potential and kinetic energies of the system as a whole. You are not worried about moving the box up and down, whereas in fluid mechanics du will be negligible. We will be only looking at potential energy changes and kinetic energy changes of the macroscopic system. So that is the only difference, otherwise the equations are the same. So I will be looking at this, so I have to express ds, and this is where S is a function of, if you want T and you have to choose your variables T and P, or S is a function of T and B. You can choose either, simply a matter of what information you need in order to calculate these changes. Normally it is convenient to choose H as a function of T and P and U as a function of T and B. Actually u is said to be a natural function of S and V, the way the equation occurs here. So Gibbs's equation of state will simply be u as a function of S and V. For thermodynamic theoretical arguments that is much more convenient, but in practice you can measure Tp or V, so you have to express everything in terms of Tv and Tp. Between these two, if you use volume you have to integrate from infinite volume, so it is much harder. For pressure you integrate from 0 pressure, so it is easier to do Tp, but your equations of state, the empirical equations that connect PVT are all explicit in explicit in V. P is a function of volume, that is how you express it, not volume as a function of P. So even if you take the van der Waals equation you have to solve a cubic equation to get the volumes, whereas pressure is given explicitly. So the more convenient variable in terms of expressions, the convenient variables are T and V, but the convenient variable for integrations are T and P. So you can choose either of them. What we will do is write down the equations for pure component systems. In the case of pure component systems I do not mind if it does not matter if I write capital H or small h, I can write it per unit mass, it is much more convenient to write per unit mass. So we will derive the expressions for dH and ds. There is a certain arbitrariness in their calculation, but that arbitrariness does not matter because you are going to find differences in entropy and differences in enthalpy. So I will derive those expressions next class.